This video will be on section 4.6, optimization. So what we'll do in this section, we'll talk about the approach to optimization, what it is, and then we'll actually work a few problems. But overall, what optimization is, or in general, it means you want to maximize or minimize some quantity of interest. So in business, some easy relatively easy things that you would want to think about maximizing would be your profit, your revenue, your income, and then if you wanted to minimize something, you would want to minimize your cost. Right? But to solve optimization problems, it will boil down to the following. We'll actually see that overall, if we can figure out the formula for the word problem, then it's just going to be a problem like last section in 4.5. But I have just some rundown here of what you do. So the first step is you want to determine an equation for your model. Sometimes you might be given an equation, but most times you're going to have to come up with it, because if not, then it's really just like last section. So I wrote if necessary here, but you're usually going to have to do that. Number two is you want to find the critical numbers, or the critical values, critical numbers, whichever one. I use them interchangeably, from your equation in step one. Now, this will happen a lot. I won't say every time you do a problem, but most of the time, since you're dealing with a real-life problem, if you come up with the correct equation, you'll probably only get one critical value. And we will call that critical value C, just to reference in the remaining. Right, but you can get more than one, in which case you would have to go through and do it like we did in the last section, but typically you will get more than one. But that is something to look out for when you do the problems. If you get two or three, and it looks like one that I do in this video and I only get one, then you might need to double check your work. But there are two ways to actually figure out whether your critical value is a maximum or minimum. One is from the previous way. I'll remind you the previous way to figure out whether you had a maximum or minimum was to make a sign chart. But we actually have something that we can do extra. Most people like this a little bit more. It just doesn't always work. But I'm going to call this the new way, because it's typically what I'm going to do. So the new way of figuring out whether your critical values are a maximum or minimum, this is a different way. You can still make the sign chart, but a new way is you can do the second derivative and evaluate it at the critical value C. So do your second derivative and plug in that number C. If the second derivative is negative, you have a maximum, and if it is positive, you have a minimum. But here, the extra thing, why you might have to rely on the old way, if your second derivative is 0, it doesn't tell you which one it is, and you must figure it out. Right. Now, to understand why the second derivative being negative gives you a maximum, and why the second derivative being positive gives you a minimum, you can look at the basic parabolas y equals x squared and y equals negative x squared. Y equals x squared has an upward shaped U-graph. We know the vertex here is a minimum. We can just see it from the picture. But if you go through and figure out the critical values of this, you'll get x equals 0. Then if you do the second derivative, you'll get the second derivative is 2, which is positive. But for the parabola, since it's such a simple shape and function, when you do the second derivative, you just get the number 2. So you don't even have to plug in 0. But that's why if the second derivative is positive, you get a minimum. And if it's negative, like y equals negative x squared, you'll get a maximum. So I just wanted to explain where those were coming from. The maximum upside down parabola, the vertex is a maximum. And if you do the second derivative of negative x squared, you get negative 2. Right, so just, if you want some understanding as to why this is the case, that is why. But once again, you can always do the old way. You don't have to do this new way. So if you get your critical values and make your number line and figure out whether it's increasing or decreasing, that works as well. And you don't even have to worry about if the second derivative is 0. So if there is only one critical value, which is how our problems will work most, if not all of the time, and it gives a minimum or maximum, then it is the absolute minimum or absolute maximum, respectively. Now, when you're dealing with real life word problems and you want to maximize something, you don't want just a local maximum, because if it's bigger at some other point, which it can be, then that's not good enough. So if your cost function has a critical value at x equals 10, and when you plug that in, the cost at 10 is like $100, just throwing out some numbers here. But later on, since you're trying to minimize the cost, maybe the cost function at 100 is only $5. Just trying to come up with an example here. Maybe you're talking about average cost or whatever. Then that means you add another critical value somewhere. So it's very important that you have only one critical value. If you have more than one, you must make a sign chart. All right, but once again, I will repeat, we pretty much only have one in all our problems because that's how most real life problems work, fortunately. And then once you determine that critical number, whether it's a maximum or minimum, it should make sense according to your problem. You just plug it in to the original function to get the actual maximum or minimum value, which is exactly what we've done before, right? So really just think about problems last section. If you have one critical number, you're doing the same thing as last section. If you have more than one, then you might have to do a little more work. But one thing I will note, just as a reminder, if you are given endpoints in your problem, you must plug those in and compare. All right, so remember last section when we were finding the absolute maximum minimums, if we had a closed interval, which means we had brackets, we searched for the critical values and plugged those in, but we also had to plug in the endpoints. So that's not something that goes away because we want the absolute extrema. All right, so that's just a reminder here. But let's go ahead and actually look at a couple problems. All right, so number one here, it says a company manufactures and sells X cell phones per week. The weekly price demand equation and the cost equations are given as P equals 400 minus 0.1x, and the cost for X cell phones is 25,000 plus 135 times X. Right, the question is, what price should the company charge for phones, and how many phones should be produced to maximize the weekly revenue? Right, so outlining here, it's asking for what it should P be. What should X be, because X represents the number of phones. And then once you figure that out, what is actually the maximum weekly revenue R? Right. Now, one important thing that we've mentioned before in this class but haven't worked in a while is the way you get revenue is revenue is your demand times your price. So R of X equals P times X. This is a formula you need to know. Actually, I kind of wrote it backwards because it's price times demand, but P represents price, X represents the demand because that's the amount of cell phones per week. The reason why we need to point this out right away is it's because that's what we want to maximize. Since we want to maximize the weekly revenue, we must find the critical numbers for the revenue function. Right? We don't want to find it for the price function because we don't want to maximize or minimize the price. We want to maximize the weekly revenue. Now, the first thing to do if you want to maximize the revenue function is actually plug in your price formula here. Right, so revenue is P times X, but we don't know how to do the derivative with more than one variable here. So we need to plug in P equals 400 times 0.1x first. So R of X equals 400 times 0.1x times X. Simplify this because we're going to do the derivative, and we know if we simplify this, it's going to be an easier derivative. So simplify, and we get, for the revenue, we have this formula 400 times X minus 0.1 times X squared. Right, so we've got the revenue, simplified revenue formula. Now do the derivative because we want the critical numbers. We do the derivative of our revenue function. The derivative of 400x is 400. The derivative of 0.1x squared is 0.2x. And then we set that equal to 0 and solve for x. That'll give us our critical numbers. All right, so I'm going to add the 0.2x to each side. We got 400 equals 0.2x. And then divide by the 0.2. And we get x equals 400 divided by 0.2 is 2,000. You can type that in your calculator to check. All right. Now, this doesn't technically get us the answer for how many cell phones should be produced. What we found is that 2,000 cell phones is either going to maximize or minimize the weekly revenue, but we need to check which one. And this is really where if you do the second derivative instead of the sign chart, it saves you a lot of time. So what I'm going to do is the new thing, compute the second derivative. Now our first derivative is right here, and doing the derivative of this, 400 minus 0.2x, is pretty quick because it's just negative 0.2. And the fact that we don't even have to plug in 2,000 here because it's just a number. So since it's less than 0, what does that mean? Since it's the new thing, I'll scroll back up and remind you, since the second derivative is negative, it's sort of like the y equals negative x squared graph in that the vertex is a maximum. So the second derivative is negative means that we actually do have a maximum. Right, but you'll notice in this problem we don't have anything but one critical value. Since we only have one critical value and we don't have any endpoints to plug in, because x could go up to infinity, it doesn't tell us stop at some point. Technically, if you think about this problem, x would start at 0. But what's going to happen if you plug in 0 for the revenue is you're going to get $0. You're not going to sell anything, so that's not helpful. So this automatically tells you this is a maximum. What we want to do is produce and sell 200 cell phones per week to maximize the revenue. So I'm going to box in all the answers to the questions over here. So x equals 2,000. I'll write the to maximize to answer the question. To maximize the revenue, we want to sell and produce 200 cell phones per week, or 2,000. Our price, if you want your price, well, this is the price equation with the x right in it, so we would just plug in x equals 2,000. So we have 400 minus 0.1 times 2,000, the price we want to sell them at. And this will give you 200. Plug that in. So, price dollars. We should sell it at a price of $200. And then the revenue, if we sell 2,000, because that's the last step, what is the maximum weekly revenue? Well, it's just P times X. So if we're selling 2,000 cell phones per week at a price point of $200, we just multiply those together and we get 4 with 5 zeros after it. But you can type that in your calculator, but this one's just straightforward. You can count the number of zeros and multiply the 2 by 2. So our maximum revenue is 400,000, and if we're talking about units here, it's in dollars. But just to overview before we got here at the end, what did we do? We figured out our equation that we wanted to maximize, our revenue equation, by taking the information in the problem. We found the critical numbers after we simplified our equation. Since we only had one, all we needed to do was do the second derivative, and notice that since it's negative, it is actually a maximum. If you got a positive, it would be a minimum, and since it's asking for the maximum here, that's really telling you that you're looking at the wrong thing. Okay. And then finally, after we figured out what x value maximized our revenue, then we plugged them in accordingly. This one we just happen to have two equations to plug in. We had to plug it into the price equation, and we had to plug it into the revenue equation as well. Okay, but that's going to be the general steps. Get your equation, find the critical values, see if it's a maximum or minimum. Hopefully it is the one that it's supposed to be. It should always be, if you come up with the equation correctly, then plug it into the appropriate formulas. Right, part B is pretty similar problem, except we want to do the same exact thing, but we want to maximize the profit. So it says, what price should the company charge for phones, and how many phones should be produced to maximize the weekly profit? Right, so it's really the same exact problem, but this time we want to maximize the profit. And then, the last question, what is actually the maximum weekly profit? Right, but what this is telling us is, like last time, we don't want to just start off and do the derivative of something right away. We need to find and simplify the profit function. Then find the critical values. Right, so remember, the profit function, P of X, is revenue minus cost. That's why you're given cost in the problem. Even though we didn't use it in the first part, we're going to use it now. The revenue, I'm going to use the simplified revenue we had for part 1. So it's 400x minus 0.1x squared. Then minus the cost. Don't forget the parentheses because you want to subtract the whole thing. Got 25,000 plus 135x was our maximum cost, or sorry, not our maximum cost, just our cost. And once again, simplify this before you worry about the derivative. It just makes the derivative easier to do. To distribute the minus sign through, we get minus 25,000 minus 135x. And if you combine like terms here, 400 minus 135 is 265x minus 0.1x squared minus 25,000. Now, as you saw with last problem, we are going to use this equation again. That's also another reason why I like to simplify, is we're going to use it at the end when we figure out the maximum profit. But this is now simplified, so we're going to find the critical values now. Right, so taking the same steps. First step, we figure out our formula. Now we're going to do the derivative of the formula we want to maximize or minimize. So the derivative of our profit is 265 minus 0.2x. And then we want to solve that we want to find the critical numbers, so we set it equal to 0 and solve to find the critical numbers. You can solve it the same way as before. Add the 0.2x to each side. And this one, since it's not a perfectly nice number, I don't know it in my head, so let's go ahead and do it in the calculator. If we divide the 265 divided by the 0.2x, or just the 0.2, we get 1,325 for x. Right, so once again, we don't want to just assume this is the correct answer, because if we made a mistake anywhere, we'll see that it will mess up in this next part. If we didn't make a mistake, then when we check if this is a maximum or minimum, it should be a maximum. But since there is only one critical value, all we have to do is the second derivative. All right, so we got our profit function here. And the derivative of our profit function, the second derivative, you'll notice is the same thing as last time, because the only thing that changes is the number from the revenue, but it's just negative 0.2. And since it is negative, that means that we actually do have a maximum. All right, so once again, if the second derivative is negative, even though we didn't have to plug in our number here, because there's no x in the formula, our second derivative is negative, so we do have a maximum. Now, there could be examples where you have to plug in x here. So if you do, you have to plug in your x as 1,325 and make sure it's negative or positive. So we do have a maximum. And then we're going to answer the questions, really exactly the same way now, except we're maximizing profit, so we have a different number, but we're going to plug in everything else similarly. So to maximize the profit, weekly profit, x needs to be 1,325. So this is the number of cell phones, remember that. The price we want to sell them at, the price is still that same formula from before. We notice we didn't affect that at all. So we want to plug in 1,325 to our price formula for x. 400 minus 0.1 times 1,325. And let's go ahead, since that's not going to be a perfect number either, do it in our calculator. And we get $267.50. Since it's talking about money, I'm going to put 0.50, but 0.5 would be good enough. And then the maximum profit, we don't have a quick formula for the profit like revenue. We have to use the formula provided for us that we figured out. So we want to plug in 1,325 For x in our profit equation, 265 times 1,325 minus 0.1 times 1,325 minus 25,000. And let's see what that comes out to be. I forgot. That is a squared. I knew that looked a little off. So minus 0.1x squared. Let's not forget that. That will definitely mess up our answer big time. And that's still a huge weekly profit, $150,562.50. And I will just, I would have to imagine this is a very unrealistic scenario because profit, when you're computing the profit of a product, you're thinking about, the cost should include not only the cost to make the cell phone, but all the people that are working on it and delivering it and all that stuff. So highly doubt you would ever profit anywhere near something like this. It's a little more than $100 profit per cell phone. Right? But that is how we go about dealing with our maximizing and minimizing profits, revenue. This equation that we're provided for cost, you wouldn't want to ever maximize or minimize that. Typically, you never try to minimize cost because it's going to be minimized at x equals 0 when you haven't sold anything. If you produce more and more, it's going to cost more and more. But the revenue and the profit definitely don't just go up as you sell some more. Think about the revenue equation. I always like to bring this up. As the price goes up, typically the number of people willing to buy it, the demand goes down. So there's a sweet spot where you can increase the price up to a point where not too many people have dropped off. But after some point, if your price is way too high, not many people are going to buy it. And we brought up the example before in a previous section, 3.7, about iPhones. If iPhones were only $100, even though everyone would buy them because they'd be so cheap, no way Apple would make any money. But at the other extreme, if they sold them for like $2,000, way less people would buy them, and their revenue and profit would definitely go down. So those prices that they sell those products for are well thought out. All right, so the next problem here simulates more so the other problems in this section where you have to come up with the equation all by yourself. Now the previous one, we did have to use that revenue was price times demand. So we did have to use that, but the price and the cost equations were given to us. This one we have to figure out all by ourselves. So it says a commercial cherry grower estimates from past records that if 23 trees are planted per acre, then each tree will yield an average of 35 pounds of cherries per season. And especially with math problem or word problems in math, I always like to point out the things that are, have numbers in them because that's probably what we're going to use. So that's why I'm highlighting that. And then if for each additional tree planted per acre up to 24, the average yield per tree is reduced by 1 pound. How many trees should be planted per acre to obtain the maximum yield per acre? And then also, what is the maximum yield? All right, so right off the bat, this one sounds a little more confusing. So we just want to, take it slow. What we want to do is start by thinking about the part I highlighted in black and not worry about what happens if we increase or decrease, talking about what's underlined in yellow here. All right, so it says if 23 trees are planted per acre, then each tree will grow an average of 35 pounds of cherries per season. So let's think about relating this to what we're interested in, which is the amount of cherries in pounds per acre. Now that's really what you would want to maximize if you were running some type of farming business, because you don't want too few trees to where you aren't maximizing your amount of cherries, but you don't want so many that the space eats up the other trees and then you don't get as much. But in the example here, the beginning 23 times 35 would be the amount of cherries per acre in that specific spot, right? Because we can have 23 trees per acre is the first part here, and then each tree at this point will give you an average of 35 pounds per tree. Right, so hopefully that makes sense. If we multiply these two numbers, then it'll give us the amount of pounds per acre. Pounds per tree, trees per acre. So let's just multiply it out. Even though I don't need this number for the problem, I still want to reference it as we make our equation. So 805. But once again, let me not put that in green because I realized I highlighted something below and the problem with that. So at this specific point, if you don't add any number of trees per acre from 23, you would expect 805 pounds of cherries per acre. Now the question is, how do we create an equation based off the yellow part? Well, this is actually going to be a lot quicker and a lot easier than it seems right now. So what you do is you start with the initial amount. So what I'm going to have here is 23 and 35. 23 representing the amount of trees per acre. Not acrea, just acre. And then the second thing in parentheses, you'll see why I added some space there in a second, but this will be representing the pounds per tree. Okay. Right, so if we do absolutely nothing to it, we would add 0 and subtract 0, because what the problem says is if we add a tree, then the average yield per tree is reduced. So let's just put a plus and minus in there. So the more trees that are produced here, the less yield we get. And then it says if for each additional tree. So let's let X represent the number of additional trees. We need to give this a variable because we don't know how many additional trees there will be. So for every additional tree per acre that is planted, up to 24 just means they don't want to add more than 24, so 47, but we don't need to worry about that right now. So for every additional tree, there is a loss of 1 pound per tree. So this is just a 1 times X. The reason I'm writing the 1 in here is because you might lose something more significant. If you lose 2 pounds per tree, then you would do a 2X. 3 pounds per tree would be a 3X. So I'll just write a little note there why I have that 1 in there. If you lose 2 pounds, do minus 2X, 3 pounds, minus 3X, and so on. But this one just happens to be 1. But you can plug in a number just to see that this makes sense. So if we increase it by 1, so up to 24X would be 1. We would have 24 here, 23 plus 1. Then since we increased by 1, the average yield would be going down by 1 pound, so from 35 to 34. And if you plug in, x is 1, you get 35 minus 1 times 1, which is 34. So it does work out. But what I want to do here is simplify my equation now. We figured out the equation, but simplify it, just like last time. We got 23 plus x times 35 minus x. I'm going to drop the 1 now, FOIL it out. 23 minus 35, I guess we're actually going to use it. I didn't even think about that. Is 805, we've already done that. Then 23 times negative x is minus 23x. X times 35 is positive 35x. And x times negative x is negative x squared. And then I'm going to just combine the like terms here. Negative 23 plus 35 is positive 12. Right, so this is the equation that we want to maximize. Right, this is the amount of cherries in pounds per acre, and we want to maximize this. In order to maximize this, this is pretty much going to be the long step of this one is figuring out the equation. Now we find the critical values and check that it's a maximum and then plug it in and everything we did in the last problem. So once you're here, once you've made the equation, the context of interpreting your result is really the only difference between all these problems. All right, so let's go ahead, since we need to find the critical values, do the derivative. The derivative of 805 is 0. The derivative of 12x is 12. And the derivative of negative x squared is negative 2x. Right, we don't really have a name for this function. You could give it a letter or a name, but we don't necessarily need to give it a name, so that's why I just wrote do the derivative. But we did the derivative, we set it equal to 0, and we solve for x. So add 2 to each side, or 2x. We got 12 equals 2x, and divide each side by the 2, and we get x equals 6. Right. So we only have one critical value again. Which means if we do the second derivative and it's negative, then it will represent a maximum. So let's go ahead and do that. Let's do the second derivative. All right, our first derivative is right here, so we're doing the derivative of what's in blue, and the derivative of 12 minus 2x is just negative 2, which is negative. Since it's negative, this is a maximum. All right, so what that's telling us, once again, we didn't have to plug in because the second derivative was just a number, but a negative number. What that's telling us is x equals 6 will maximize the cherry output. So it'll maximize the amount of cherries per acre. Right, and now I'm just going to scroll back up to reread what the question's actually asking for. It asks for how many trees should be planted per acre to obtain the maximum yield, and what is the maximum yield? All right, so our equation is the one we created right here. This will give us the yield of cherries. So we're going to plug in x equals 6 to here to get the yield. And then how many trees per acre? Well, that's just this portion here. So we plug in x equals 6 to this part. So the trees per acre, let me write the to maximize portion. So we're just figuring out our answers now. The formula for the trees per acre was 23 plus x, and we want x equals 6. 23 plus 6 is 29. There should be 29 trees per acre planted. And the maximum yield, now the maximum yield is not the pounds per acre, so don't plug it into just here. It's the whole thing. This whole equation is the yield equation. We want, the maximum total. So the maximum yield, so the first part was the 23 plus x, which is 6. The second part was 35 minus x. And for x, we got 6. Both of these work out to be 29, which is coincidental. But 29 times 29 is, I'm just going to write 29 squared. It's easier to write in the calculator, 841. Right, so what we just figured out is if we plant 29 trees per acre, we should expect a yield of 841 pounds of cherries per acre. That's an increase of 36 from this 805 the cherry grower started with. And that can make a huge difference, in any type of business, because that's a pretty big increase, right? But once again, it's really important once you figure out what number your critical value is and that it actually works, that you plug it into the correct thing and interpret the results, right? So like I said, we can repeat it again. I don't care to plug in the 6 just into this part. I don't care how many pounds per tree we get specifically. The question doesn't ask that. It asks just how many trees should be planted per acre, and then what is the maximum yield per acre. Right, so make sure you're just careful with that. All right, so there's a couple, there's 2 or 3 problems in the homework that look like that. This third one might seem a little different, so we're gonna make sure we deal with that as well. It says starting with a 200-foot stone wall. So once again, so anything with numbers, I just like to underline. A farmer would like to construct a rectangular enclosure. Well, the fact that it's giving us a shape is pretty important, but there is a picture in this problem, which I will show you in a second. By adding 800 feet of fencing, as shown in the figure, so it's provided in the problem. I'm not going to draw it for you and have it not be in the problem. And this is labeled in the figure, so once again, this will make sense when I draw it. Find the values of x and w that result in the greatest possible area. Right, so when I draw the picture, the reason why this problem is something you want to solve is that when you have a rectangular enclosure, if you want to make the biggest possible area with the least amount of fencing, that's the least amount of money to enclose some area. Right, so this is the way the enclosure works. So what it does is there's a fixed 200-foot long stone wall that's there. And then the rest is filling out a rectangle like this. All right, so the 200-foot stone wall is just part of the rectangle. What this is saying is the total amount of extra here is 800 feet because they have 800 feet of fencing. So the orange part adds to 800 feet. I know that's definitely not the right 2. And then the letters X and W. Now forgive me, I don't remember exactly which one they call X and W, but let's say X is the bottom part and W is the side part. What they want to do is figure out the X and W that result in the greatest possible area. Right, now very important, what are we even trying to do here? Well, we want to find the greatest possible area, which means we want to maximize area. And we're talking about a rectangle here, so we want to maximize the area of a rectangle. Right, so the formula for the area of a rectangle, we know that's what we need to write down. I'm just going to use A for the letter. And the area for a rectangle is length times width, but the length and the width are represented by X and W in the problem. Right, so we want to maximize this formula, which means we would want to find the critical values. We want to do the derivative. But what's one problem with this? We don't know how to do the derivative with two different letters. Okay, so how do we fix this? How do we actually figure out this question? If we don't know how to find the derivative with two different letters, well, what we're going to do is kind of depart from number one, even though this is a totally different problem. I'm going to scroll up because we did run into that problem before. In number one, we had the revenue formula was P times X, but we happen to be given the formula for P. All right, now in our problem here, we're not given another formula, but we are given something else to figure out. We are told that there's 800 feet of fencing, and that'll actually help us solve for X in terms of W and plug it in. So what we want to do is write a perimeter equation, then solve for W and plug in. It sounds like a lot, but start by writing down what is the formula for the perimeter of a rectangle. Well, the perimeter is just the total length on the outside, so the perimeter is all the sides added up. Right, the perimeter is all the sides added up. Right, come to think of it now, I think the picture, I apologize, it doesn't matter where it's at, but I think they actually put the X, oops, on the top side next to the 200. So I'm going to just readjust that. We haven't done anything with the formula, except this would change our area formula because the length of this side would be 200 plus X. I apologize for that, but I think that the way they have the picture drawn is actually like this now that I'm remembering it. But it really doesn't make a difference which way X is written. I just want to make sure I do it the same way. All right, so the perimeter is adding up all the sides up. But the top side is 200 plus X. And remember, the bottom side would exactly match that. So we have two of them, the top and bottom, plus the width. The other two sides is 2 times W. So let me just label that. This is the top and bottom. All right, this is how long each the top and bottom is. And then since we have two of them, that's where the 2 comes from. The 2 times W comes from the left and the right. Right, each length is W. Now here's the thing you want to be careful on is what does it add up to? It doesn't add up to the 800 because we have this 200-foot stone wall. It adds up to 1,000. Okay. So, I would guess, especially doing all this problem, that the main reason this problem is done incorrectly is you do all the steps, but it's so easy to just see that 800 and forget about the other 200 or what it's saying. All right, but now what I'm going to do is exactly what we have here. I have my perimeter equation. I'm going to solve for W and plug it in. We're going to distribute the 2 here. So we get 400 plus 2x plus 2w equals 1,000. Solve for w, which means get everything besides the w by itself on the other side. We're going to subtract 400 and the 2x. And we got 2w equals 1,000 minus 400 is 600 minus 2x. Now to get w by itself, we divide each side by 2. Easiest to just display it as dividing everything by 2 here, and we get w equals 300 minus x. All right, but that's what we want to plug in. And once we do that, then we can actually approach it like the previous problems. All right, so I'm going to go ahead and plug that in. We got 200 plus x, and then the w is 300 minus x. Because we're doing the derivative of this, even though we know we could just use the product rule here, I'm going to distribute, FOIL it out, and simplify like I always do. So 200 times 300 is 6 with 4 zeros after it, 60,000. 200 times negative x, negative 200x. X times 300 is 300x. And x times negative x is negative x squared. All right, and then combine like terms and simplify. So negative 200 plus 300 is 100. All right, we've done a lot, but now we have the area formula, the one we want to simplify. The one we want to find the critical numbers of and maximize, finally simplified. So this is finally ready to do the derivative of. All right, so you can just do the derivative. You can write the notation, dA over dx or something. Maybe I'll write it that way. But if we do the derivative here, derivative of 60,000 is 0. Derivative of 100x is 100. And the derivative of x squared is 2x. We did the derivative. Now we find the critical values by setting it equal to 0. Subtract the 100 on each side. We got negative 2x equals negative 100. And we divide each side by the negative 2. And we get x equals 50. All right, so we did the derivative and we got one critical number like all the rest. So this is either a maximum or minimum, or where it's occurring rather. So now, like we checked the other ones, we do the second derivative. And because we're looking for what are we looking for here? We want the greatest possible area. We want to maximize. So we once again hope the second derivative is negative, and it is. The derivative of 100 minus 2x is just negative 2. So it is a max. After all that work, see the calculus part is the quick part, which is the case a lot of times in word problems. But we got x equals 50. Now it says find the values of x and w that result in the greatest possible area. So we got x. What is w? Right, it doesn't want the actual area, it wants x and w. And we have a formula for w here, and we can actually plug that in. So we plug in x equals 50, and we get w equals 300 minus 50, which is 250. So we do get our x and w values. All right, but once again, I know I apologize for the confusion again at the beginning about where x was, but I remembered as I was drawing it and going through this that the x is actually right there. Right? It could have been down here. You could still do it, but your perimeter equation would have been a little bit different. It would have been just x on the top and bottom. and then you would have had slightly different answers here, but it would have worked out the same way. Right, but once again, that is really optimization. These are the main three different kinds of problems. Ones where you're given most of the formula, ones where you're trying to maximize some type of product yield, revenue, things like that. And then this final one, definitely the most challenging one because you have this 200-foot wall. If you didn't have this 200-foot wall, it'd actually be much quicker. But unfortunately, we have it.